Okay, very good afternoon to one and all. Last class we have been discussing about prime numbers, right? How to find whether a given number is prime or not. Actually, we had the discussion in order to understand these theorems called Fermat's theorem. It is also called as Fermat's little theorem. Shortly, they used to call as Fermat's theorem. So this theorem is used to find the solutions very easily, and you can also use this theorem to find the multiplicative inverse also. We have discussed that we can able to use our extended Euclidean algorithm to find the multiplicative inverse. Similarly, we can also make use of Fermat's theorem also to find the multiplicative inverse. There are different versions of Fermat's theorem. The first version you can able to see here. That is, if you have any integer a risen to a power of p minus 1, it will be congruent to 1 modulo p. And here the p is a prime number. Okay, that's why we discussed how to find the prime number in the last class. So P stands for prime number, and if you find any integer risen to the power P minus 1, it will be congruent to 1 modulo P. That is, this is the prime number and this P minus 1 should be the power of this integer. So you can blindly write the answer will be running to 1 because I hope everyone knows how this congruent operation works. Right. Second version, okay, there's nothing but if you multiply A on both the sides, you'll be getting this one. That is, any integer risen to power p, which is a prime number, will be congruent to a modulo p. Okay, under one condition is nothing but the integer which you are going to take and the prime number, okay, both should be relatively prime to each other. Relatively prime in the sense the GCD between these two numbers should go for 1. Right. Under these conditions, you can able to solve the numericals easily using these two theorems. Okay. We'll see an example here. Here they're asking you find the result of 6 power 10 modulo 11. Here your p is 11 and your integer is a is 6. And you can able to see a power is nothing but it's p minus 1, that is 10. So you can blindly write 6 power 10 modulo 11 as 1. You can cross check this using a calculator also. If you go for 6 power 10 and you take mod 11, it will run to 1. This is the first question of Fermat theorem. So if you go for the second example here, they are asking you to find the result of 3 power 12 modulo 11, and here your value of a is 3 and the prime number p is 11. So which version you people can make use of here? Any idea? I want everyone to note down these two formulas, I mean expressions with these two expressions. I want everyone to note down. After noting down, kindly raise a hand. Okay. Once noted down, kindly raise a hand. Have you people noted down these two formulas, the two theorems? Okay. So now I want you people to tell me how we can able to solve this 3 power 12 modulo 11. Anyone have your first version or second version? You can go with both the methods. Okay. If you are going with any one version, can you people let me know? How there'll be a slight modification is required. That's all. Nothing much. If you people can able to tell at least put which version you're going to proceed with in your chatbots. Am I audible, guys? Which version we can proceed with this one? Yeah. Okay. You can go with both version 1 as well as version 2. So version 2 is nothing but a power p will be congruent to congruent to A modulo P, right? So here, but this is not, we don't have A power P. Here instead I have A power P plus 1. So what I have done in the sense I have splitted them into two versions, that is 3 power 11 into 3. So I'll be doing 3 power 11 modulo 11 into 3 mod 11. So 3 power 11 modulo 11 is looking like your second version of your permanence theorem, which will obviously gives me a result as 3. And 3 modulo 11 also gives me 3 as answer. So 3 into 3 is 9. 9 modulo 11, I'll be ending up with the answer is 9. Right. Now we can able to find the multiplicative inverse. If you take the first version, I mean if you go with the first version or your second version, and if you divide by your a, if you take your first version divide by a on both the sides, you'll be able to get your this part multiplicative inverse. That is, if you want to find a multiplicative inverse of an integer a with respect to modulo p, let's say inverse, this is a multiplicative inverse, right? The multiplicative inverse want to find means simply find a power p minus 2 modulo p. This answer will give me the multiplicative inverse of A with respect to modulo P. For example, here you can able to see, I mean, without using your external algorithm, you can also go with this method. In examination, if we mention that you have to go this particular method, means then you have to find the multiplicative inverse using this particular method alone. You should not go on your own. If we didn't mention anything in the question paper, then you are allowed to use any method to find the multiplicative inverse of any integer, right? So in this example, they are asking you to find the multiplicative inverse of 8 with respect to your modulo operator 17. So here simply 8 power p minus 2, because your prime number is 17. So p minus 2 gives me 8 power 15 modulo 17. So can anyone tell how we can able to solve this 8 power 15? Like, is it, are you people able to do this using a calculator? 8 power 15 modulo 17. People are saying yes. Can you raise a hand? So I can able to solve this 8 power 15 modulo 17 in my calculator. Yes, I need some response from you, because based on your feedback only I can able to teach you how you can able to solve. If no response, then it's none of my business to teach you these things. Right? I'll just proceed with the syllabus itself. That's all. In examination, don't come and blame me, say how can I able to solve such bigger numbers kind of thing. Don't come and ask me. Assuming that you people are well versed with finding this higher degrees at 8 power 15 modulo 17 and proceeding, right? So if you solve this 8 power 15 and modulo 17, you'll be getting as 15 mod 17. And similarly, like 5 power minus 1 mod 23, again it is p minus 2, 5 power 23 minus 2 mod 23, you'll be ending up with your multiplicative inverse. So if you want to cross verify here, just take this 14 and multiply with 5 and take your modulo 23, you'll be ending up with the answer as 1. Right. So with this, we are concluding my Fermat-Trinity theorem. Next, we are going to Euler's theorem. Before proceeding with Euler's theorem, you should be very clear with what you mean by Euler's phi function. Right. So this Euler's phi function is also called as Euler's torsion function. Okay. And this Euler's function plays very important role in cryptography, especially in key generation process of modern cryptographic techniques. So this phi function will be denoted like this one, phi of n. So what are the properties of this function? Okay, people have to remember this one. That is, if you take phi of 1, the answer will come as 0. And phi of p, and if p is a prime number, the answer will be p minus 1. And if you have two integers, that is, you can able to write an integer as a product of two integers like phi of m plus phi of n, then I can able to write the answer as phi of m cross phi of n. And here you can able to see m and n are relatively prime. Relatively prime in the sense the GCD between this m and n should go with 1. That is, if I can able to represent any integer as a product of two integers which are relatively prime to each other, yeah, then you can able to use this phi function with third property. And the fourth one, if you have phi of p power e, p is a prime number, and when e is any arbitrary integer, okay, then I can able to write phi of p power e as p power e minus p power e minus 1. Right. So these are the basic properties you people have to remember regarding your phi function. I want everyone to note down these four properties, because with these four properties only we are going to learn the Euler's theorem. So I want everyone to note down these four properties. Once noted down, kindly raise your hand. Kindly note down these four properties. Like how we have Euler's, Fermat's theorem. That is, you have two versions and one multiplicative versions. Those three formulas should be there with you, along with this Euler's torsion functions properties. These four properties. Once you people have noted down, kindly raise your hand so that I can proceed. Thank you, Akhil. The only one. And then also, I mean, this is a, how this fourth property has been formed. Okay. Suppose they're asking you to find the value of phi of 13. So 13 is a prime number. You can use your second property there. So phi of 13 is 12. So what is the value of phi of 10? So phi of 10, you can't go with 10 minus 1 because 10 is not a prime number. But I can able to write this 10 as a product of two integers like 5 plus 2. And at the same time, this 5 and 2 are relatively prime, right? Relatively prime numbers to each other. So I can write this phi of 10 using third rule as phi of 2 multiply the phi of 5, and you can able to see this phi of 2 is a prime number and phi of 5 is also a prime number. So you can use your this property that phi of p here is nothing but p minus 1. So phi of 2 will be coming out as 1 and phi of 5 will coming out as 4. So answer is 4. Right. Can you people tell what will be the value of phi of 240? So phi of 240, how can I able to represent this phi of 240? Any idea? I'll be giving you a hint. This is using a fourth property. We can able to incorporate this fourth property along with other properties also, like this one. That is, you can able to write, if you take your common factors here, HCF, right, you'll be getting this one. So you can write a 240 as 2 power 4 into 3 into 5. So if you take phi of 240, I can able to write it as phi of 2 power 4 multiplied with phi of 3 multiplied with phi of 5. So this is nothing but p power e. So p power e I can write as p power e minus p power e minus 1. Right. So this 2 power 4 minus 2 power 3 will be getting multiplied with the, here you can either you can apply your fourth property directly, okay, like p power e, or you can go with your phi of p also. Both are applicable, because if you see phi of p is p minus 1, here also you can able to see 3 power 1. Even if you apply your fourth property, it will be coming at p power e minus p power 1. So 3 minus 3 power 0, 5 minus 5 power 0. It will be getting as 3 minus 1 only. And here 5 minus 1. It will be same as your second property. Right. So at last, we'll be getting an answer as 64. Right. So how many of you are clear with the Euler's phi function? Can you raise a hand? Thank you, Vishal. Only one. What about the others? If people have any doubts in this Euler's phi function, you can ask me. Assuming that you are clear, I'm proceeding. So this is a yes or no question. Can we say phi of 49 as phi of 7 into phi of 7, which comes to 36? Is this question correct or not? True or false? Can we say that yes or no? Just tell me answer whether it is yes or no. Can we say that phi of 49 is phi of 7 plus phi of 7? You can use your chat box and they can let me know the answer. Can we say this yes or no? I hope you get my question. Rishad, yeah, no. Mubarak Ali, no. Okay. People are supporting Rishad and Mubarak. You can put like button to them. Thumbs up button. If anyone saying yes, can you come up? No. Okay, so no is the correct answer because here if you apply your four, I mean your third rule, simply phi of 7 into phi of 7. Okay, this is not m cross n, it is m cross m itself. Because both are same here, and so they are not literally prime to each other. So here you'll be using your instead of using a third rule, you'll be going with your fourth rule. That is representing your 49 as 7 square. So p power e minus p power e minus 4. So answer is 42. Right. I hope now you people are clear with Euler's phi function. Right. And this Euler's phi function can also be used to find how many number of elements. I mean, I'm not saying that what are the elements, how many number, the count, how many number of elements are present in any z n power star. Simply, if you find phi of n, the answer will let me know how many number of elements are present in the particular Zn star. So I hope everyone knows what is Zn star is. We just saw a set of integers, set of residues, and set of elements which have only multiplicative inverse will be there in Zn star. So Z14 star, how many number of elements? Simply if we take phi of 14, I can write as phi of 7 into phi of 2, which is something like 6 into 6, totally 6. Totally 6 elements will be there, and these are 6 elements 1, 3, 5, 9, 11, and 13. So here, one thing people can able to remember easily: if n is greater than 2, okay, always your phi of n will be even number. You can check your phi of n will be even numbers. Here 6, here it is 42, here it is 64. If n is greater than 2, here is 4, and here it is 12. Whenever your value of n is greater than 2, then obviously all my phi functions will give me an answer in even number. If you're getting an odd number, then you have gone wrong somewhere. Right. Now we move on to Euler's theorem. So it may look similar to your uh, Fermat's theorem, but here the slight difference in sense, here we are not taking anything with respect to prime numbers here. One of the drawback we can't able to say, uh, handicap of Fermat's theorem is nothing but you can able to see here, whenever your modulo operator is prime alone, I can able to use my Fermat's theorem. Suppose if your modulo operator is not a prime number, okay, it is some random integer, then you can go with your Euler's theorem. So what does this Euler's theorem says in sense? The first version. Otherwise, if you take any integer a and this power is phi of n, it will be congruent to 1 modulo n. This is your first version. Second version, okay. If you are having an integer a which is assigned to any random constant integer called k times phi of n plus 1, it will be also congruent to a modulo n. Okay. The second version plays major role in a crypto system called RSA crypto system. Okay, we'll see this in our upcoming modules. The second version plays a major role in one of the famous cryptographic technique. It is still in use called RSA crypto system. So here they are asking you find the result of 6 power 25 mod 35. So 35 is not a prime number, so we can't able to go with your Fermat theorem. So simply I'll go with Euler's theorem. The first condition you'll be checking in the sense whatever the modulus you have, take this modulus, find phi of that modulus. In this case, phi of 35 is phi of. How will you find phi of 35? How come you'll be getting this one as 24? You can write as phi of 7 into phi of 5. So you'll be getting a 6 cross 4. So 24. You can able to see this is also 24. Simply I'll apply my first theorem. The answer runs for 1. Second one. Find the result of 2 power 62 mod 77. Right. In this case, if you find mod 77, can anyone tell what is the answer for mod 77 here? And use your chat box. Mod 77. What is the answer? So not mod 77, 5 of 77. Sorry. 5 of 77, what is the answer? Okay, Rishabh, 60. How many of you getting 60 or anyone getting other than 60? Okay. Dinesh Sharma and Rishabh, you're getting is 60 because 77 you can write it as 5 of 11 into 5 of 7, right? So you'll be getting as 10 into 6, you'll be getting as 60. But in this case, you can able to see this is in 62. Okay, this is not mandatory that you have to go with second version. Even if you want to go with first version, what you can able to do since you can write 20 square mod 77. I'm speaking from examination point of view. Into you can go with the first version 20 times 60 mod 77, which will run for 1, and this you can use a calculator and you can find the answer. If you want to go with second version, so I want before everyone to note down this two versions as of now, because I want everyone to keep this as a handy one page. You have your Fermat's theorem or Totient, Euler's function. That is your 5 functions, 4 properties, and Euler's theorem. Everything in a single paper, being an open book examination, you can have these things. Yeah. Note down these two theorems, you can raise your hands, guys. So I'll explain that second example. Because while explaining, I want you people to have this theorems with you. That's why. So once you people are noted down, raise your hand. Yes, Vikas alone, everyone. What about others? Because once noted down, I'll move on to the next slide. Okay then, right. So here, if you want to use our second version, the second version you can able to see the expression is a power k times phi of n plus 1. Okay, it will be congruent to a mod by n. So here, what they took in the sense they took this k to be 1 in that particular example. So they got it as 20 power. So k is 1 means 20 power 1 times phi of n plus 1 mod 77. So this one came as 60, 2 power 61 it will come because phi of n is 60. So 20 power 61 mod 77 will be ending up, and this part. And you have 20 power 62, you simply have 20 mod 77. So this one will run to answer of 20. This one will give you answer of 20. So 400 mod 77 you can use a calculator and you can able to get the answer directly. Right. So these theorems also you can able to apply. For example, if you see while finding the multiplicative inverse and all in Fermat's theorem, like you are getting a 60 power 99 mod 101, 22 power 209 power 2 double 1. You can use your theorems. Even you can use your Fermat's theorem here. Okay, even you can go with your Euler's theorem if it is satisfying your phi of n concept. Okay, because here if you apply the 60 power 99 mod 101, phi of 101 is simply 100. You have 60 power 99 here. Right? You can't go with it. Otherwise, you have to, because if it is 101, you can go. But if you see this case, 211, you'll be getting 210. Again, I have one shortage. So at this time, you can go with your Fermat theorem or and I think if not, there is a method we will be discussing in the upcoming classes. Right. For this one, I was asking you people whether you know any method to this one. No one responded. So you can also make use of Euler's theorem to find the multiplicative inverse. Because if you take the Fermat's theorem, you can able to find the multiplicative inverse one and only if your modulo operator is prime. Okay, in the case of Fermat's theorem. If it is a non-prime number, you can go with your Euler's theorem to find the multiplicative inverse. And this is the method. That is, your A inverse modulo n will be equal to A power phi of n minus 1 modulo n. Right, if you take the same examples like previous case, okay, here if you are able to asking for multiplicative inverse of 8 over modulo 77. So we just saw phi of 77 came to 60. Here we'll be ending up with 8 power 59 mod 77. How can you find this 8 power 59 mod 77? There is a method. Is there any easy way you can able to do it using calculator itself? Any idea you people are getting? Can you tell me? That is, you have to find me is 8 power 59 mod 77. If you people are getting any idea, post it in the chat box. So I'm not getting any idea means just raise your hand so that I can help you. I can guide you. Using a calculators itself, instead of going to theorems also, you can use your calculators to help you in these cases. Any simple way, any idea people are getting? It's like a divide and conquer method only. Simple way can solve this. Or shall I provide the solution? If you want a solution from myself, can you raise your hand at least for that? Okay. So if you people have a calculators with you, I want a few help from your side. What is the if can you people able to if you put 8 power 59 mod 77, what is the answer your calculator is giving? Is it giving the direct answer? 8 power 59 mod 77. I'm asking your calculators like your scientific calculators instead of laptops or system. If it is giving the answer directly, can you raise a hand? That is your calculator. Sir, my calculator is giving the direct answer 8 power 59 mod 77. Can you raise a hand? Guys, please respond. Yes, no, any one response. No. So can you people tell the highest power what you people can able to solve in your calculator for this example? Can you people get the answer for 8 power 10 mod 77? Is it possible? 8 power 10 mod 77. If it is possible, post the answer in the chat box. 8 power 10 mod 77. If it is not possible, at least put it's not possible in the chat box. 8 power 10 mod 77 in your calculator. Eight power 10 mod 77 ways, some response. It won't take that much time. Okay, I'm moving on to next topic. Okay, I'm fed up with this one. Next one is Chinese remainder theorem. Okay, so how we can, what is this Chinese remainder theorem in sense? It is used for solving the congruent operation. Okay. Whenever you're going to have parallel expressions like this one. That is, if you have your x on your left hand side, okay, you can able to see for all this expression, your left hand side is same. That is x. But it is congruent to a different integer called a1, but different model called m1. So a2, m2, these things are different, but your left hand side are all same means you can able to solve these expressions parallelly. This method is called Chinese remainder theorem. Okay, we'll see how this Chinese remainder theorem works on. So before this one, I want everyone to note down this expression. This general expression. We'll be having x, which will be congruent to a1, a2, and goes on up to ak, and m1, m2 up to it goes on mk. At least if you want to take a screenshot, a picture, anything, you just take it out. So once you have noted down this expression, kindly raise your hand. I hardly give you a 1 minute time for this one. Have you people noted? Noted means kindly raise your hand so that I will proceed. So this is used to speed up your modular computations in Chinese similar theorem. Okay. Even if you have any modulus like M1, you can able to split them into multiples of M1, M2. I can use this Chinese remainder theorem. You'll see how with an example directly. So here they are saying that this set of equations, that is there are unknown number here called x, it will be congruent to 2 modulo 3, and this is congruent to 3 modulo 5. And if you substitute the same x here, it will be congruent to 2 modulo 7. And they ask you to find the value of x. Can you people tell? The trial and error method also you can tell. That is, if you substitute this x for all these three expression, then all the three expression will be holding good. Whatever the value of x, you're putting here, the same value of x will be substituted here also. But here, it will be congruent to 2 modulo 3. Here it will be congruent to 3 modulo 5 and 2 modulo 7. So can you people tell any wild guess what will be the value of x here? Any guess? It's like a trivial question, like a puzzle only. There is one number which will satisfy all these three expressions. If you get the answer, you can post it in the chat box. So if you're feeling difficulty, for example, here in this expression, if we substitute the value of x to be 23, you can able to see. So 23 will be congruent to 2 modulo 3, right? In this case, in place of x, if you substitute 23, and if you take 23 mod 3, the answer will be 2. And same 23, if you take mod 5, you'll be getting 3. And same 23, if you take mod 7, also you'll be getting the value to be 2. So this is how, for this kind of expressions, we can able to use Chinese similar theorem. For example, how we are going to use the same thing using solution using Chinese similar theorem. The first step, what we will be doing in the sense, we'll be creating a common modulus. We call it capital M, which will be product of M1, M2, and Mk. That is, if you remember the general expression here, this one, the product of this M1, M2 up to Mk. Okay, that's the first step. Step, you have to compute k number of values called M1, M2, and up to Mk, such that your capital M1 will be the common modulus which you found by multiplying these values divided by M1. And M2 will be this again the capital value of M divided by M2 and goes on up to Mk values. The third step is nothing but you have to find the multiplicative inverse of these M1, M2 up to Mk, all these multiplicative inverse for these values, and you'll be naming them like this with their respective modeling. That is multiplicative inverse of M1 with respect to small m1 here, multiplicative inverse of capital M2 with respect to small m2, like this multiplicative inverse of Mk with respect to the small mk. So now we have three values here, capital M, and here capital M1, M2 up to Mk's, and here multiplicative inverses of M1, M2 up to Mk. And comes the solution equation here. That is, you can able to find the value of x here. Sorry. Able to find the value of x here by simply multiplying a1. So a1 is nothing but this part here. Congruent values. So a1 multiplied with m1 multiplied with m1 inverse plus a2 m2 multiplied with m2 inverse and goes on, okay, up to this one. Then the entire thing will be taken under a modulo operation of your common modulus here. So if you see this example here, in the first step you have to find the common modulus m. Common modulus m is multiply 3, 5 and 7. I'll be getting 105. Then I'm computing capital M1, capital M2 and capital M3. Okay, which is nothing but your capital M, which is 105 divided by your small. This is your small m1, m2 and your m3. So 105 by 3 I am getting 35, 105 by 5 I am getting 21, 105 by 7 I am getting 15. Now you have to compute the multiplicative inverse of this m1. M1 with respect to, capital M1 with respect to small m1. That is, you have to find this 35 multiplicative inverse of this 35 with respect to modulo small m1 3. Right. Then you have to find your multiplicative inverse of this 21 with modulo 5, which is m2. Then you have to find multiplicative inverse of 15 with modulo 7. And here you can use any method of your wish. These are prime numbers, so I hope you can use your direct your Fermat's theorem here, or you can go with your Euler's theorem also. Euler's theorem, if you go with the Euler's theorem, you'll be getting up as you can phi of n minus 1, right? Phi of n is 3, phi of 3 is 2, 2 minus 1 is 35 mod 3. Because you'll be getting this one. You will get the answer. 35 mod 3 if you take, you should get answer is 2. And here 21 power, 21 inverse modulo 5. Nothing but phi of 5 minus 1. Phi of 5 is 4. 4 minus 1 is 3. 21 cube mod 5 will give me the answer for multiplicative inverse of 21. And similarly 15 power minus 1 mod 7 is 15 power phi of n minus 1. So 6 minus 1 is 15 power 5 mod 7 will give me the answer for this one also. So it is found to be 2, 1 and 1. And at last to find the value of x, they took this a1. Okay, this is a1. This is your a2. This is your a3. So a1 times your capital m1, which is 35. Multiplying the inverse of this one is 2. Then a2 is 3. Capital M2 inverse. This is a3. Right, capital M3 and the M3 inverse. And if we solve this one and if we take modulo 25, we'll be ending up with the answer as 23 here. Anyone have any doubt in this Chinese remainder theorem? If it is clear, raise your hands. If you have doubts, you can ask me. Chinese remainder theorem is worthy for 10 marks. Fermat theorem will be getting for 10 marks. Euler's theorem also is worthy for 10 marks. Anyone have any doubts with respect to these three theorems? You can ask me now. All these three theorems are clear to you people. Can you raise your hands once again? So these three theorems, we are clear with the concept. Can you raise your hands? Right. So we can also able to represent this equation like this. Instead of writing this equation like this, we can also give you questions like this. Find an integer that has remainder 3 when divided by 7 and 13, and it is perfectly divisible by 12. Right, that is you have to find an integer, so that is x be congruent to, will be getting a remainder 3 when divided by 7 and 13. So this is the first expression. 7 and 13 going to give same congruent, that is 3 mod 13, and it is divisible by 12, so x will be congruent to, divisible means you don't get any remainder, so 0 mod 12. Right, so with this you people have to solve this numerical. So I want everyone to solve this numerical and let me know the answer in the next class. Right. Okay, there's also other way we can able to ask this one. Here, assume that you need to calculate z, and z is in the format of x plus y, and given you the x and y are 123 and 334. But your system is going to accept only numbers less than 100. This is your system which you're going to design, or your cryptographic algorithm will be able to get, can able to operate only with 2-digit numbers. It can't go with the 3-digit number. That's the condition here. So what should we do in the sense? Here therefore, creating two expressions with respect to this x and y. They give you x as 123 and y as 334. And they're saying that it will be able to accept numbers less than 100. So you can able to create 4, 5, any number of equations, but I prefer 3 equations is more than enough to find the answer. So the highest 2-digit number is 99, next is 98, 97. So if you take 123 and if you take mod 99, you will be getting 24 as the answer. Am I right? 123 mod 99 will give me the answer as 24. Again, if you take mod 98, I will be getting 25, 97, 26. Similarly, I went for y also. mod 99. 334 mod 99 will give me an answer 37. Okay, 334 mod 98 will give me 40. 334 with mod 97 will give me 43. So these three expressions you have created. So here the given one hint is nothing but the value of z is x plus y. So we'll be getting a final expression like this. I'll be adding these two expressions, x plus y. That is 24 plus 37 mod 99. We'll be getting a 61 mod 99. 25 plus 40 mod 98 will be giving me 65 mod 98. 26 plus 43 mod 97 give me 69 mod 97. So now you have to start solving this expression to find the value of z. These are three different ways we can able to ask a Chinese remainder theorem. Right. So once you only issue here in the sense you have to end up with creating this expression. Sometimes we provide you with the direct expressions like this numerical, or we have like this. We can able to give you direct expressions, or sometimes we used to give like this, or sometimes you'll be getting expressions like this. Right. So you have to use your logical mind to get the expression. Then you have to solve for your Chinese remainder theorem. Right. So anyone have any doubt in these things? You can ask me now.